storm-generated weather system collided along the Atlantic coast of the United States and Canada on December 27th, the day immediately following the earthquake. Tide gauge records showed that the two separate wave systems, the tsunami traveling from the opposite side of the planet and the local storm surge generated by ordinary Atlantic weather, coalesced along the shores of Maine and Nova Scotia specifically. Combined 19,000 kilometers from where the ocean floor first ruptured, a tide gauge in Callao, Peru, recorded a wave larger than the one that had struck an island just 1,700 kilometers from the epicenter itself. 24,000 kilometers away, in Halifax, Nova Scotia, a wave measuring nearly half a meter rolled in more than 31 hours after the earthquake first struck, having traveled the entire length of the Indian Ocean, curved around the southern tip of Africa, and journeyed the full span of the Atlantic to get there. This is not a story about a wave that hit one coastline and stayed there. This is the story of the December 26, 2004 Indian Ocean tsunami, an event so physically enormous that scientists eventually confirmed it had been recorded on more than 100 tide gauges scattered across the Pacific and Atlantic Oceans, thousands of miles from where the disaster actually began, arriving in places nobody had any reason to expect a tsunami warning at all. Stay with me on this one, because the physics behind how a single wave can genuinely cross three separate oceans is one of the more remarkable and honestly undertold parts of this entire disaster's story. Drop a comment and tell me if you remember where you were when you first heard about the 2004 tsunami, because I think this event left a mark on an entire generation in a way few natural disasters ever have. And if you want to keep learning about how global disaster monitoring has evolved since this event, subscribe now, because the infrastructure built in its aftermath genuinely changed how the world tracks these threats. Let's start with the earthquake itself, because its true scale is genuinely difficult to grasp even now, more than 2 decades later. At 7:58 in the morning local time on December 26, 2004, a magnitude 9, 3 megathrust earthquake ruptured off the northwest coast of Sumatra, along a stretch of the Indian Ocean where the Indian and Australian tectonic plates dive beneath the Burma microplate. That magnitude places it among the largest earthquakes ever recorded anywhere on Earth, and the rupture itself was almost incomprehensibly long, tearing along roughly. The resulting tsunami went on to kill more than 225,000 people across a dozen countries, and left at least 1 million more homeless, making it the deadliest tsunami ever recorded in human history. It's worth understanding exactly what a megathrust earthquake actually is, because the term describes something genuinely distinct from a more typical earthquake most people picture. Megathrust earthquakes occur specifically at subduction zones, where one tectonic plate is forced beneath another, and they're capable of producing the single largest earthquakes anywhere on the planet precisely because of the sheer scale of fault surface that can rupture at once. Rather than a single, relatively contained section of a fault suddenly slipping, a megathrust event can involve hundreds of kilometers of plate boundary rupturing in a single, continuous sequence, releasing an almost incomprehensible amount of stored tectonic energy within just a few minutes. That specific mechanism, an enormous elongated rupture along a subduction zone, is also precisely why megathrust earthquakes are so consistently associated with the most catastrophic tsunamis in recorded history, since the vertical displacement of the seafloor across such an enormous rupture area displaces an equally enormous volume of ocean water directly above it. Here's why this earthquake genuinely earns the description nobody saw coming, and it's worth understanding the specific institutional failure behind that phrase, because it wasn't a failure of science. It was a failure of infrastructure. In December of 2004, there was no tsunami warning system covering the Indian Ocean at all. The Pacific Ocean had operated a coordinated multi-nation tsunami warning network since the 1960s, built specifically in response to earlier Pacific-wide disasters. The Indian Ocean had nothing comparable. Seismologists around the world detected the earthquake itself within minutes. Its magnitude was substantial enough to register on instruments globally, but there was no established communication protocol, no coordinated alert system, and no clear chain of authority to translate that seismic detection into an actual actionable tsunami warning for the coastal communities about to be struck. In several of the hardest hit regions, the tsunami's first waves arrived before any meaningful warning had reached the people in its path, sometimes with only the earthquake's own shaking, or the ocean's own strange, sudden recession from the shoreline, serving as any warning at all. If you found that explanation of megathrust earthquakes genuinely useful, a like on this video helps more people understand exactly why certain earthquakes produce such catastrophically large tsunamis while others of a similar general magnitude produce comparatively minor ones. Let's talk about what actually happened along the coastlines closest to the rupture, because the devastation there unfolded with almost no time between the earthquake and the wave's arrival. Coastal communities in Sumatra's Aceh province, the closest populated region to the epicenter, had only minutes before the first waves struck. International survey teams that later assessed the disaster zone measured run-up heights, the difference between the ocean's normal level and the maximum height, the water, reached inland, exceeding 20 meters along Aceh's northwest coast, with one specific location recording a maximum run-up of 51 meters, an almost unimaginable wall of water surging inland. Thailand's coastline saw run-up heights between 5 and 20 meters. Sri Lanka and India recorded run-ups between 4 and 12 meters. And in a detail that captures just how far this disaster's reach genuinely extended even within the Indian Ocean basin itself, more than 5,000 kilometers away, along the coast of Somalia in East Africa, survey teams measured run-up heights approaching 10 meters, a genuinely lethal wave striking a coastline most people wouldn't have associated with this disaster at all. Now, let's trace exactly how this tsunami actually left the Indian Ocean entirely, because this is where the story becomes genuinely remarkable from a pure physics standpoint. If you've made it this far into the video, subscribe now, because the journey this wave actually took across the globe is genuinely one of the most fascinating pieces of oceanographic science ever documented in real time. According to research published by scientists at NOAA's Pacific Marine Environmental Laboratory, the tsunami's energy didn't simply dissipate once it had finished devastating the Indian Ocean's coastlines. It continued propagating outward, curving around the southern tip of Africa, and from there splitting into two separate paths, traveling up through the Atlantic Ocean, one branch heading toward the coast of Brazil, the other continuing north toward Nova Scotia, Canada. Scientists studying tide gauge data documented that these waves, having already traveled more than 24,000 kilometers across the Indian Ocean, and then the entire length of the Atlantic, still arrived at Halifax with a measurable wave height of 0. 43 meters, a genuinely significant amplitude for a wave that had crossed nearly 2 full ocean basins to get there. It's worth understanding exactly how a tide gauge actually manages to detect a tsunami wave at all, particularly one that's traveled tens of thousands of kilometers and arrived with an amplitude measured in mere centimeters, because the sensitivity of this measurement technology is genuinely remarkable in its own right. A tide gauge continuously records the height of the ocean surface at a fixed coastal location and normal tidal fluctuations, driven by the gravitational pull of the moon and sun, and typically produce smooth, slow, predictable rises and falls over the course of many hours. A tsunami wave, even a genuinely small one by the time it's crossed an entire ocean basin, produces a distinctly different signal, a comparatively rapid, oscillating pattern with a much shorter period than normal tidal movement, superimposed on top of that regular tidal curve. Trained researchers can identify that distinctive tsunami signature within the broader tide gauge record, distinguishing it from ordinary tidal movement even when the actual physical wave height involved is small enough that nobody standing on the beach at that exact location would have noticed anything unusual happening in the water at all. Here's the detail that genuinely defies most people's intuition about how tsunamis actually behave. And it's worth sitting with directly because researchers themselves specifically flagged it as one of the more surprising findings from their analysis. You might reasonably assume that a tsunami wave gets steadily weaker and weaker the further it travels from its source, fading out gradually with distance the way ripples in a pond eventually flatten out. That's not what the data actually showed. Researchers found that larger tsunami amplitudes were recorded at Callao, Peru, roughly 19,000 kilometers east of the epicenter, than at the Cocos Islands, sitting only 1,700 kilometers south of the epicenter itself. Similarly, the wave amplitudes recorded at Halifax, Nova Scotia, thousands of kilometers further away than the Cocos Islands, were also measured as larger. That counterintuitive pattern reflects the genuinely complex physics of how tsunami energy actually propagates across an ocean basin, influenced heavily by underwater ridges, basin geometry, and the specific direction the initial rupture's energy was focused, rather than simply weakening in a smooth, predictable way as distance from the source increases. Let's talk about the Pacific Ocean specifically, because the tsunami's reach extended there too, adding a genuine third ocean basin to this disaster's documented global footprint. And if you found that explanation of how tide gauges distinguish tiny tsunami signals from ordinary tidal movement genuinely fascinating, like on this video, helps more people appreciate just how much careful, painstaking scientific work went into confirming this wave's truly global reach. Research published in the journal Surveys in Geophysics specifically examined tide gauge recordings along the Pacific and Atlantic coasts of North America, locations more than 20,000 kilometers from the source area, and confirmed the tsunami had been accurately recorded at tide gauges throughout the world's oceans, not simply within the Indian Ocean basin where the devastation actually occurred. According to NOAA's own Science on a Sphere program, more than 40 tide gauges throughout the Indian Ocean recorded the tsunami directly, with a maximum documented amplitude of 1. 75 meters at Port Blair in the Andaman Islands. But beyond that immediate disaster zone, the tsunami was also recorded on more than 100 separate tide gauges scattered. Across the Pacific and Atlantic Oceans combined, a genuinely staggering geographic footprint for a single seismic event to leave behind in the scientific record. There's a genuinely strange and tragic postscript to this story, specifically involving the Atlantic coast of North America, because the tsunami's arrival there happened to coincide with an entirely unrelated weather event. And if you've made it this far into the video, subscribe now, because the sheer coincidence involved in what happened next along the Atlantic seaboard is genuinely one of the more remarkable details in this whole story. Storm-generated weather system collided along the Atlantic coast of the United States and Canada on December 27th, the day immediately following the earthquake. Tide gauge records showed that the two separate wave systems, the tsunami traveling from the opposite side of the planet and the local storm surge generated by ordinary Atlantic weather, coalesced along the shores of Maine and Nova Scotia specifically, combining to produce genuinely damaging waves exceeding 1 meter in height. Researchers noted that the incoming tsunami waves were further amplified specifically by the broad underwater shelf off Nova Scotia's coast, a detail of local underwater geography that happened to work against the region at the worst possible moment, superimposing tsunami oscillations directly on top of storm-induced surge and producing flooding that local hydrographic officials directly attributed to that combined effect. Let's put some actual scale to just how far these waves ultimately reached along the eastern coast of North America specifically, because a separate, dedicated study analyzed more than 100 individual tide gauge records stretching from Florida all the way up to Nova Scotia. Canadian researchers conducting that analysis found that the tsunami was identifiable on most of the outer tide gauges across that entire stretch of coastline, with maximum wave heights in the northern regions measuring between 32 and 39 centimeters, and maximum heights in the southern regions, closer to Florida, measuring between 15 and 33 centimeters. In the northern region specifically, researchers noted that the impact of these tsunami-like waves was more than doubled by that same major storm system moving along the eastern seaboard at the exact same time. A genuinely unfortunate coincidence of timing that amplified the tsunami's already remarkable ocean-spanning reach into something with real, measurable physical consequence along a coastline thousands of miles from Sumatra. Now let's talk about what actually changed in the aftermath of this disaster, because the scale of the institutional failure that allowed this earthquake to go so completely undetected by any coordinated warning system led directly to one of the most significant overhauls in the history of global disaster preparedness. And if you found the Nova Scotia storm-tsunami collision genuinely surprising, subscribe now, because understanding how the world actually responded to this disaster is just as important as understanding the disaster itself. In the years immediately following the 2004 tsunami, the international community, coordinated substantially through UNESCO's Intergovernmental Oceanographic Commission, established the Indian Ocean Tsunami Warning System, a coordinated multi-nation monitoring and alert network specifically modeled on the kind of infrastructure that had already existed in the Pacific for decades. That system now links together seismic monitoring stations, deep ocean pressure sensors capable of directly detecting a tsunami wave as it crosses open water, and coordinated communication protocols specifically designed to ensure that the next major earthquake in this region triggers a genuine, actionable warning within minutes, rather than leaving coastal communities to rely on the earthquake's own shaking or the ocean's own eerie retreat from shore as their only warning. It's worth understanding a bit more about how this new warning infrastructure actually functions day to day, because it represents a genuinely significant technological achievement built specifically in response to this disaster's failures. The Indian Ocean Tsunami Warning System now incorporates a network of deep ocean pressure sensors, instruments resting on the seafloor capable of directly detecting the subtle pressure changes caused by a tsunami wave passing overhead in open water long before that wave ever reaches a populated coastline. That data gets transmitted in real time to regional warning centers, where it's combined with seismic monitoring data to rapidly assess whether a given earthquake has actually generated a tsunami, and if so, how large it's likely to be by the time it reaches specific coastal communities. This entire system, largely absent in December 2004, now provides exactly the kind of coordinated, rapid detection and communication infrastructure that could have given Indian Ocean coastal communities genuine, actionable warning time, the single missing piece that turned this specific earthquake into such a uniquely devastating disaster in the first place. Let's talk about why an event like this genuinely matters for anyone living anywhere near a coastline today, regardless of which specific ocean happens to border your own home. This disaster fundamentally reshaped how scientists and emergency planners think about tsunami risk on a truly global scale. rather than treating it as a regional hazard confined to whichever specific ocean basin an earthquake happens to originate in. The scientific confirmation that a single tsunami could be measured on tide gauges across 3 separate ocean basins, thousands of kilometers apart, demonstrated with genuine, undeniable physical evidence that a sufficiently powerful earthquake anywhere on the planet carries the theoretical potential to send a measurable wave to coastlines an entire hemisphere away. That understanding directly informs how modern tsunami warning systems are designed today, with international coordination and data sharing extending well beyond the specific ocean basin where any individual earthquake actually occurs, precisely because the 2004 event proved so conclusively that ocean basin boundaries offer no real protection against a tsunami powerful enough to cross them. So what should you actually take away from understanding this event in this level of detail more than 2 decades after it happened? If you've made it this far into the video, subscribe now, because there's genuinely more to understand about how global disaster science has evolved since this event reshaped it so fundamentally. First, understand that the warning systems now protecting most of the world's ocean basins exist directly because of the catastrophic gap in coverage this specific disaster exposed, and that gap has been substantially, though not necessarily completely, closed in the years since. If you live anywhere near a coastline, understanding whether your specific region falls under an active, coordinated tsunami monitoring system, and knowing your local evacuation guidance if it does, remains genuinely worthwhile precaution, regardless of how distant the nearest major fault system might seem. Second, understand that a tsunami's danger doesn't necessarily correlate cleanly with distance from the source, given the genuinely counterintuitive amplitude patterns researchers documented during this exact event. Larger waves recorded thousands of kilometers further from the epicenter than smaller waves recorded much closer. And third, understand that international scientific cooperation, tide gauge networks, coordinated data sharing, and shared monitoring infrastructure represents one of the more effective, if quieter, responses to a disaster of this scale, transforming a catastrophic, largely unwarned tragedy into the foundation for a genuinely more resilient, more globally coordinated warning infrastructure protecting coastlines the original disaster never even touched. Here's the thought I want to leave you with, and it's worth sitting with for a moment before we close this out. Most people who remember the 2004 Indian Ocean tsunami remember it, understandably, as a regional catastrophe, a disaster that devastated Indonesia, Thailand, Sri Lanka, and the surrounding coastlines within that single ocean basin. That memory is accurate, and it's also, in a genuine scientifically documented sense, incomplete. What the actual scientific record reveals is something considerably larger and stranger, a single seismic event powerful enough to send a measurable, physically documented wave. Curving around the entire African continent, splitting to travel the full length of the Atlantic Ocean, and registering on tide gauges along the Pacific coast of North America as well, arriving in places separated from the original earthquake by not one, but 2 entirely different oceans. It's worth ending on one final, genuinely humbling piece of context, because it puts everything covered in this video into its proper scale. Even with all of the scientific analysis, the tide gauge data, and the decades of subsequent infrastructure improvements this disaster directly inspired, the 2004 tsunami's true toll remains, in some ways, still not fully known. Official death toll estimates range from roughly 227,000 to as high as 230,000 people. A range that itself reflects the genuine difficulty of accounting for every single life lost across a dozen countries, many of them in remote coastal communities, where record-keeping infrastructure was limited even before the disaster struck. That uncertainty isn't a failure of science. It's an honest acknowledgement of just how vast and how genuinely global this single morning's destruction actually was, stretching from villages in Aceh province that most of the world had never heard of, all the way to a tide gauge in Halifax, Nova Scotia, quietly, recording a wave that had traveled nearly the entire circumference of the planet to get there. The earthquake that nobody saw coming didn't just devastate a single region. By the time its waves had finally finished their journey, they had left a measurable, undeniable physical signature in 3 separate oceans, a genuinely global reminder of just how connected and how vulnerable every coastline on this planet ultimately remains to a disaster that begins thousands of miles away.